Welcome once again. This is the lecture number 8 on the deep learning. In this session, we are going to talk about the introduction about the neurons. We are going to see some of the history related to the neuron and some of the biological perspective of the neuron. So this is what the architecture of the general neuron people talk about into the biological area. They says that there is something called nucleus, and nucleus is something we can think that here some processing is going to happen. So there is some nucleus where some, as I told you, that some processing is, we think that there is some processing. So what he is going to process? So information is coming to the neuron nucleus. Information is coming to the nucleus from dendrites. So there is something called dendrites. From the dendrites, some information is coming. So if you want to see the what is the architecture of the dendrite, so dendrite is something like this thing. Okay, so there are some connectors like this. Okay, so you can see that here also there would be this kind of thing, and here at every end there is something like this kind of a structure is there. So they are the dendrites. So you can see that multiple dendrites are there. Okay, so they are bringing something to the nucleus, and now nucleus is doing some kind of processing, and the output of this actually goes to the axon. So axon has some kind of link also, and after that there are a terminal, because this is the point where they terminate. And if we see the structure of these axon, this is going to be something like this. Okay, so there is something like this kind of structure that is into the axon. So we can think that we can think it in this way, that this is the nucleus. From this nucleus some output is going, and at the end we have something like this. Okay, this is the axon terminal, and there is another neuron over here, and this neuron is going to get the input from here. So this dendrite is going to be connected in this particular way. So this is what the structure is. Generally this structure, actually they are going to be connected, and this is called the synaptic connection. The connection that they have is called the synaptic connection. So what happens that if there is, if this particular nucleus does some kind of computation and makes the high input, because into the next one it can send some impulse signals. If it want to send some impulse signal, what happens, ultimately there would be some there would be some particles that actually transfer from here to here. If the particles are transferred from here to here, then they travel, then you can think that they are going to increase the concentration at this particular place, and therefore they are going to diffuse, and by this they reach to the next next nucleus. So this is the general architecture that that actually, as we have discussed, involves a cell, and then output axon, synopsis connections that we have talked about, that this is a synopsis connection that they have. There are molecules that when one neuron want to send some signal to another, they actually transfer the molecules, and dendrites are the ones which actually receive this thing. Any questions on that? So these things are actually a kind of broad structures, and we have actually, human brain typically has 10 to the power 11 number of neurons. That is going to be a very large number, and what we think that each of them is connected to 10 to the power 4, means 1000 of other things. So if there is one neuron, it is going to be connected to 1000 other neurons. So output means axon terminal, how many connections would be there? Around 1000 connections they are going to make on an average with the other thing. Okay, so if we want to find out that how good these things are with respect to the nowadays the computer system, because into the computer system we also model the same thing as a neuron. So if we create a computer system, so you know that our computer system has a very high speed. They can operate in 10 to the power minus 9 seconds. Okay, if one instruction is around, it takes 10 to the power minus second. However, humans actually take only 10 to the power minus 3 second. If they take 10 to the power minus 3 second to switch. So if I have a computer that has this much speed, and my human neurons are actually going to have this much speed, so you can see that there is a very huge gap between the performance. The huge gap is going to be between these two things. If we create the same kind of dense structure which actually the human brains have, and we deploy our our technology, our computer technology into the system to take the switchings, so it is going to be very very fast. However, we have seen that even with this kind of fast speed, even with this kind of fast speed, nowadays computers are not fast as compared to the humans. So humans are very fast as compared to the machines, because if you want to measure in terms of taking decision, for example, when the humans are driving the car, they are taking the decision in very less speed, so very less time. However, if you deploy a computer for that, it may take longer time to decide that what action it should take. Why it is happening? It is happening because the kind of connections that actually these neurons have, and that we actually say that it is a neural networks. Once again, neuron, when we talk about the neuron, it is a single unit, okay? And the neural network means it is a network of the neurons. So multiple neurons are there. So how the neurons are connected, if we want to find out, so you can say that if there is one neuron, as I told you, that it is going to be connected with 1,000 other things in our human brain. Then this one is again going to be connected to 1,001. This one is again going to be connected to 1,001. It is also possible that this is also connected to here. We are not sure about this, but mostly it is going to be like this. So diagonal and other kind of connections are also possible into the human brain. So human brain is very complex kind of a structure, and how to train these kind of things, we are not much aware about this. That's why how they are actually trained. There are philosophy that tells that in this way the things are going to be trained, but we are not actually able to train on those kind of arrangements. So we actually develop a kind of simple architecture, and we say that I am going to put the neurons into the layer wise only. Okay, our neural networks contains the thing into layer wise only. However, human have a much dense kind of connections over there. So since we don't know that how to find out the right parameter, if the connections are very haphazard or very general kind of connections are there, so we are actually we are limiting our, by this we are limiting our computers to have the limited capacity. Maybe sometime we would see that into the later classes, that how can we build this kind of general computers. And look, these things are actually when they are modeled in our actual systems, they are called as a energy based system. So those things are very complex to be trained. And when initial at the initial time when we were actually developing neural network based system, the community was developing neural network based system, at that time people tried to develop these kind of model. But again, the problem was only this, that finding out the right parameter for these kind of architecture was difficult. So the idea was actually dropped. Now, and people started working on these layered kind of architecture. But recently, a few years back, we into the community, people are again talking about this kind of architecture. So let us see that how much time it is going to take to again go to the general kind of architecture. Once again, why I wanted to, what a point I wanted to make, that humans are more densely connected systems, and that's why even with the smaller with the systems having the smaller lesser inferior kind of switching time, these computers are actually these systems are actually better. Human systems are actually better as compared to the computer ones. uh, if we want to see that what how the development sir, recording was not started. Okay, okay. So if we try to understand that how the development was with respect to these neural network based system has happened, so there are few important things that actually take very important points, such as Macaulay experiment that we are going to discuss very soon, Medline system development. These things take very important point. So let us come to this particular slide where uh, and try to understand that what is the history of neural networks. So when I'm going to talk about the history of the things, I'm actually talking about with the perspective of neural network only. Okay, so let me tell you something. So it was 1872, long back, when the people actually tried to first understand that how our nervous system is our nervous system is. So it was on the biological level. People tries to analyze that how the tissues are there, means they actually come up with the understanding that in the human brain there are something called neuron, and they are actually connected with each other. So this kind of understanding that there exists neuron and there is a cell and there is a output and then there is a input kind of thing is possible, something is going to inside and taking the decision. This biological kind of experiment was happened long back around 1872. However, this was a biological understanding and it was not related to in any way to the computation. So the computation model actually was proposed by Macula and Pitt. They actually gave the idea that looks like that into the, because here the understanding was only this, that neurons are there and they are connected. But what is the relationship? How can we define in terms of the computation? Actually, this work was actually done by the McCulloch and Pitt around 1943. And you please remember that what is this particular time? You know that first generation of the computer was available in 1945, second generation 1955. And the first generation computer means the valves, you know that the diode valves were there. And second generation, when the transistors transistors and diodes were used. So these were system, these at that time when this experiment was actually happening, and this is long back I'm talking about. So even the computer were not available at that time. It was very it was very big system. So even a small computation if you want to do, so multiple room, it requires a very big setup of the multiple rooms. At that time he had proposed that looks like that there is some centralized entity, and in this centralized entity uh, something is going inside. And he was telling that these things are a kind of strength. He was telling that there is strength. So if there is one neuron, it is connected with another neuron, and one neuron is connected, this is another neuron connected with this neuron. So all these connections have some different strength. He was thinking in the terms that they have strength, and all of them have a different kind of strengths. Okay. So if the strength is different, then if the same amount of thing is being sent from this node and this node, so if this strength is higher, so it is going to make more impact on this particular neuron. So this was the model that was given by McCulloch and Pitt. After that, people were started thinking that let's assume that this is what I have. So over the period of time we keep learning. So how can we model that, what is learning? Okay. So people started thinking in terms that how can we model the learning into this particular system. So Hebbian learning, the concept of Hebbian learning was actually introduced by Donald Hebb around 1947. And it is something like this, that look, I told you that there are few neurons and there are other neurons and other neurons, and they are very differently connected. They are connected in very they may not be connected into the layered way. So there is some connection. So if something is being input, I'm not sure about this, that where things are input. Let's assume that something is coming from your visual system, and this is connected to neural network. So this part is neural network. Okay. I want to find out that what is the how can I define that, what is the strength? So McCulloch had defined that there is a strength. How can I tell that what is the strength at that particular place? So he proposed this idea that what output you want. For example, you want to raise your hand or something, some action you want to do. So there is some neuron that actually gives the order with respect to that. So try to see that what is the connection of this particular neuron with the previous things. Okay, if this is connected with these kind of line, so he was telling that if this is the line that actually take part into the decision, then strength of this particular line is going to be increased. Means this would become more thicker. You can think that this connection is going to be more thicker. Make sense? So this is called the Hebbian learning. Then after a few years, I think into after few next year itself, there was a concept called cybernetics that came. And this is again an interesting concept, that you know that you know that what happens that into the diodes you may have seen that, for example, if it is a PNP diode, so what happens that you know that there are something called biasing and PN and PN. I'm not actually drawing the right diagram over here, so because I'm not sure about this, actually what happens that in into the PN junction kind of thing, what happens that if you increase into the signal, a small increase you do at this particular place, there will be huge increase into at the other part. Have you seen that? So uh, because you know that this is the same time when after when the diode and other things has been diode and transistor has been invented. So they thought that there could be some direct relationship between the input and output. If you want to do the output of, you want to get the output of this thing, you need not to by yourself spend that much power to change this to the signal to this quantity. You only have to only do this much change, and this is going to be magnified and your things are going to be better. So cybernetic actually tells that there should be a multiplying factor that actually can multiply the thing, and then the things can be actually related. So if you want to do this much change, you what you need to do only this much change. Using this kind of idea, people thought that okay, if this kind of idea is there, then then there is one neuron and it is connected to another neuron, so there should be some weight, so that if if it is this particular neuron is going to provide this much change, at the end there is more change is going to be produced. So the concept of weight actually started coming. So around 1954, Frank Rosenblatt actually proposed the perceptron. This is what actually we have studied into the last class, and the idea was very simple. As we have seen that it is only the linear decision boundary where there is a one processing unit and multiple inputs units, for example x1, x2, x3, x4 are actually there, and they have the weight w1, w2, w3, w4, and then it does the summation and gives you the thresholded output. So this kind of architecture was then, using this kind of understanding of the weight, was proposed by the uh, Frank Rosenblatt around 1954, and this was a wonderful actually proposal. And because after getting this kind of proposal, many of the newspapers at that time, they started making hype that okay, we have actually solved all the problems. So you know that initially the development is very less, and but people are actually less excited. But after this thing, there a lot of excitement into the actual community actually grown, that okay, we can do many things. And as I told you that international newspapers etc., they have written at that time itself that perceptron has been proposed, and now we can develop the system that can talk that can talk to each other. We can develop a system that can have the computer vision and whatnot. So everything was proposed like that. So a lot of hype was actually generated by this. One such system was developed at that time. So you know that at that time people were talking using telephones. So in the telephone system, what happens now? Whenever, for example, when you are talking from one phone to another, so if you are speaking something at this particular place, so that voice goes to here, and from the receiver it may again come back to you also. So you would be listening a kind of echo in your voice. So it would be very difficult to talk. So this was, however, the system was developed, but it was very difficult to talk because there was lot of echoes were happening into the system. So the first system that using neural network was developed was the Medline, and it actually removes the. It was an adaptive kind of filter that was removing echoes from the system. So it was a very good thing that something was has been proposed on that. People started solving the problem of computer vision using these perceptron. And in that time, there was a very interesting experiment that was done by Habel and Wiesel around 1962. This experiment actually was a kind of very destructive kind of experiment where there was a cat, and uh, whether my cat is good, I don't think. So there was a cat, and some electrodes were actually entered into his brain, and there was a screen. On this screen they were actually showing some of the images to the cat. They were expecting that when they would show the image of a rat. So I'm very bad in drawing, okay, I'm sorry for that. When they show the image of the rat to the cat, they were thinking, or milk to the cat, they were thinking that at the time these uh, these electrodes are going to record some high excitement. But surprisingly, when they have shown the images of a milk or cat, the sorry, or mouse, the system, the electrodes were not showing high effect. However, when they were actually changing the images, when there, for example, there was an image of chair, and when they removed the image of chair and put the image of apple, at that time they were seeing that there is some excitement happening into the some signal is coming from the electrodes. So Hubble and visual experiment is very important in the sense that they were thinking that when the things are stable on the screen, at that time our neurons did not fire. Our neurons fire when there is some change. So in the change, what are the things that humans are what the things which are actually noticed by the system? So they had understood that looks like that the corner points are important, because now here the corners are actually moving. So they understood, and they had given the understanding that corners point are important. Okay, when the things are actually moving, at that time our neurons actually get fired. Okay, so we right now in this scenario we have perceptron, and we have made a system also with that, and we have more understanding about the computer vision. So but since the paper has many in the newspaper are telling that give me a system that can do the computer vision task like that, but the people were not able to do that computer vision kind of task. So they actually tried to develop complex systems. So they started developing complex system. They were telling that I am going to put the uh, perceptron in one layer, then I'm going to perceptron into another layer, and then I'm going to combine them, and by this I can create the neural network kind of architecture, and then I can make the bigger system. So this was a proposal by Frank Rosenblatt once again. So it was actually around 1965 they proposed that there should be a multi-layer perceptron, and multi-layer perceptron are going to have the higher power as compared to the single one. Okay, so more studies has been done, and next paper was actually, this is a very interesting paper that was proposed by the Minsky around 1969, and he have actually explained the similar concept with some of the examples, and actually using the XOR example, he has shown that if you because you know that we all know that this perceptron is a linear decision boundary. So if the data is like this, that where if data is like this, that where one side there are positive examples, the another side there are negative example, then we can draw a line. But if something happens like this, where this positive examples are here and negative examples are here, if this is what the example is, so I cannot draw any line over there. So he have mentioned this particular thing in his paper. However, his paper was actually not on this particular thing, that it is a limitation. He was trying to suggest that this multi-layer perceptron solution is actually needed in this kind of scenario. So in this scenario, however, we cannot draw a single line, but using multiple line, two lines, we can tell that if whether the item is above both the line or below both the line, and then we can decide, or in between one line and another line. Then by this we can apply some logic and tell that whether the item is positive or negative. So this idea was actually proposed over here, but this paper was actually wrongly interpreted by the society. They thought that many of the paper again started talking about that no, neural networks are not good and they cannot perform these kind of operation. This was if XOR kind of example is there, now these kind of problem cannot computer cannot solve, and this actually lead to a huge decay into the popularity of the neural networks at that particular time. One very difficult thing at that particular time was also this, that however you know that it was proposed that multiple layers you can put, if you put the things into the multiple layers, you can do the things. It was suggested, but the point is this, that because let's assume that this particular one is connected over here. Just focus on any of the weights. For example, I want to find out what should be this weight. So how do I know that what should be this weight? How can I change this particular weight? Actually, this was not known to anybody. So this was the biggest problem, that how to set up this weight was actually very difficult. So even if this idea was there, but no one was able to implement that thing in an effective way. Around 1986, the concept actually which other peoples were using, called back propagation, was adopted in the neural network society, in neural network peoples. So they thought, they used this idea, and they told, what is the back propagation? That if you do a small change in this particular W, then you try to see that what is the change into the output. So the change between the output and two different values, the difference between them, you divide by this rate of change. So ultimately, what I wanted to tell, that you want to see that what is the gradient, with respect to this particular W. You can use that gradient and propagate backward, and by this you can update this particular value. So we would come back once again and into full detail of this back propagation algorithm when in just few classes after this, that how this back propagation work. Very important algorithm. So when the back propagation was actually came into the existence, means into the adaptation, at that time it becomes again possible to train these kind of models. So whatever problem people were actually having, it got solved, and now we were able to train the bigger model. However, again, there was a problem that anything that have more than 4 layers becomes very difficult to train, because you may have heard about something called, people talk about the vanishing gradient problem and exploding gradient problem. Again, these things would come into the much detail into the later classes. Because of those reason, again, it becomes very difficult to train more than the 4 layers. But at least for the till the 4 layer it was possible. So again, the people started developing interest into the domain, and it was again a very good time. And you can see that from 69 to 86, it was a huge time. It is 17 year, people, nobody was talking about the neural network, and they were thinking that neural network had actually died. After that, in 1989, yeah, there come a very important influential paper that talks about the universal approximation theorem. What does it mean? You know that if you have a function and you provide x, y, for example, any number of parameter, let me just write x, and x representing the multivariate. So let's assume that on the x there is some function. So this particular paper says that I can give you a neural network circuit that also take the value and of the same value x, and gives you something as output. And the difference between fx and nx, I can make it as small as you wish. Okay, I can make this difference as small as you wish. So what does it mean? That any function, if you give me any function, I can give you equivalent neural network circuit for that, and with a very high accuracy, that on the data, all the data point, it is going to have the same value. So it was a very interesting paper, very interesting thing. And this again actually increased the, what we say, the confidence on these kind of architectures. So it was a good time, people were talking and solving the thing. And however, the progress was very less, because as you know that nowadays the things are working and they need a lot of hardware, and those, that many number of hardware support was not available at that particular time. Around 1997, okay, LSTM, that nowadays many other peoples are using as a RNNs, these things once again would come in larger detail in later classes. In the later classes, LSTM was actually proposed in 1997, way back. 1998, Lee Kuhn has proposed the convolutional neural networks on the MNIST database. So let me just also tell you something about this, that how difficult this particular time was. That, so you know that Windows came around when Windows, have you heard about something called Windows 97? Windows 97. So this was a kind of earlier Windows 95 version was actually out. People were using Windows 95, and then Windows 97, then Windows 98, and then Windows 2000, then Windows XP. I'm just talking about the some of the software that were available earlier time. Windows XP. So this came in 1998, 1995, 1998, 2000 XP. So this time was very difficult for the peoples. Okay, if you ask anybody who was at that particular time that what was the scenario, so they don't know that when maybe your computer is on right now, and if you close it and shut down it and you restart, you would not be able to restart the computer once again. No, anything could happen with your computer. Things means memory was not that much reliable, software was not that much reliable. So however, these kind of techniques which I'm talking about, that LSTM and convolutional neural network were developed at that particular time, 1998, 1997. You can see that in this particular same point of time, but nobody was able to execute. Means in general, the no people were not able to take it forward because of the limitation from the hardware and the software point of views. This is a very interesting paper, and let me tell you that this would come many other time to you. And this is a very interesting architecture, and I wanted to just let you know about this. And this is, you know, that if you have you sent a postcard to anybody? In the postcard, there is a place to write the address, and after that, there is a place to write pin code. So somebody has actually taken lot of pin codes and cut all these digits, because there is a place where you can write a digit, cut all these things and digitized. And by this he created a database called mnest integer digit database. And on this particular database, what architecture the person should use, the Lee Kun, who is the pioneer into the computer science domain, you know, that into the deep learning domain, he's a pioneer. So he has actually provided the architecture where he was telling that that provide this image, and then I think, I'm not sure about this, maybe 17 cross 17 image, then you apply the CNN kind of architecture on that, and then do the pooling, and the same kind of modern architecture he had proposed at that particular time. But still, as I told you, that because the hardware and software support was not that much available at that particular time, so people actually forget about that particular thing, and people started thinking that no, we if we want to solve our problem, we should go into the handcrafted method only. And then people were talking about the handcrafted method. So at that time, again, even these things were high, but again the hype was actually down, and nobody was talking about that I'm going to use neural network. If you talk anybody, he was be telling that no, I don't want to use the neural network, they are not going to work. And this, we have talked about this particular duration. So people started actually working on the handcrafted method. Handcrafted method means they by themselves, by seeing the data, they by themselves decide a technique that in this way you should find out the feature. So there was a very interesting and celebrated algorithm that came around 2004 called SIFT, Scale Invariant Feature Transform, by David Lowe at that particular time. And many other time people were using like this, and many other algorithms, SIFT, SURF, ORB, and many other methods people were actually trying at that particular time. So this time was actually full of the full lot of activity was happening that was actually related to the handcrafted method. But however, in between, the hardware capacity also started increasing, and hardware capacity and software capacity both combined, and lot of data, availability of lot of data, actually make the things possible, and the people started increasing this concept once again. So around 2006, there was a very important paper that talks about the unsupervised pre-training. So this particular paper was talking about that if you are having a neural network and you want to find out what is the parameter that should be there, so you should not think that how to find out these values. There are automated ways to find out these values. So again, using backpropagation only. So using these kind of paper, again started discussion and the requirement of the good software into the domain. In that time, speech recognition also gave the very good results, and using this similar kind of neural network architectures, the speech recognition was actually able to give the good kind of result. Fifi Lee and their community has actually thrown a challenge into the computer science domain, and they have invested huge amount of money, and they have thrown a challenge called ImageNet challenge, where they have created a very huge database of the images, and that contains more than 10,000 categories. Do you understand what do you mean by category? So in an image there is a cat. So it is so out of these images, this how many images contains cat? Cat is a category, dog is a category, elephant is a category, car is a category, bus is a category. So how many categories? There are many categories, but they have thrown they have collected a very huge database, and they have thrown a challenge on 10,000 images and asked for that, can you give me a best system on this particular database? So multiple people started doing the experiment, and our community actually was involved in that. So people were solving this particular problem with their handcrafted method. And at that time, very important thing I wanted to tell you, at that time, the error on this particular database, on this particular ImageNet database, was 26%. 26% was error. Around 2010, the error was 2010, and 2011 the error was around 26%. And they were using all handcrafted methods such as shift, surf, orb, and whatnot. LXNet, very interesting thing I'm going to tell. LXNet use the same convolutional net kind of architecture, same convolutional net kind of architecture, and the trained it on the ImageNet database. And by this, he was able to reduce the error by from 26% to 16%. It was a huge jump. So the system becomes very good. So everybody got interest into that how to do that, because earlier what was happening now, earlier error was around 28%, then it becomes 26%. People were crawling on the errors, but suddenly the error became 16%. It was a eight layer architecture, on that they got this kind of result. Next year somebody came and told him that, okay, this 8-layer architecture that you have made, you have not optimized it. If you optimize is better, then you would be able to get 12% error rate only. So means, because this was the first thing, people just proposed this, that 16% error is there. So with the small changes on his architecture, with the 8-layer architecture itself, the error could be reduced to further 12%. It was again a very big thing, that you can see that into 2 years the error from 26% to become 12%. New network was called the ZFnet, and the LXNet was the, and the Alex Krajewski has proposed the network, this one that was actually given the 16% result, and this architecture was called the LXNet. So from LXNet we reach to the ZFnet. So if you are on this ZFnet, so once again try to just help me to understand that what I'm telling. I'm telling that there was a very big database. There was a very big database. Once again, 1 minute. 2010, okay, 2011, 2012, 2012. So this, the error was 28%, then 26%. Suddenly the error becomes 16% with the 8-layer of the architecture. Somebody told, okay, you have not optimized the things. If you can optimize it well, it could be 12% error. ZFnet. So can you tell me that what would you do if you were into this scenario? What would you do? You would definitely like to increase number of layers. So why I am using 8-layer? Let me use 16 layers. Okay, VGG 16, and the error reduced to 7.3% only. Next year, Google came into the competition, and again he have proposed a network called Google LeanIt, and he thought that why I am only increasing the number of layers, why not I am seeing the things from the different scale. Different scale means, for example, if this is an image, if you reduce the size by half, so it is a different scale. Okay, so if you reduce those things by half, so what would happen, that you would be focusing on the different parts of the things. So size of seeing the things from the different scale variation. So it has not only increased the number of layer, I think number of layer were 22. Then using this method, by increasing the by applying the things, and by applying the concept that I'm going to see the things from the different size, the error was able to they were able to reduce the error to 6.7%. And again, this as I told you that in this particular time 2004, there was a paper on SIFT from David Lowe. Okay, this paper was very successful only because of this particular reason, that he was also seeing the things from at the different scales. So ultimately people definitely want to utilize this experience into this network also, and by this they were able to get the better accuracy, 6.7%. After that, suddenly a very radical idea came. ResNet, from the Facebook. What was the idea? Idea was this, that let's assume that you have a network circuit. Let's assume that you have a network circuit that works well on this particular data, some networks layer you have. So what if I put more layers on this? Whether the accuracy is going to increase or decrease? Can you tell me? Increase or decrease? If I put more layers, whether they would increase or decrease? Can you type? Let's assume that you got some accuracy on this particular size. So if I put more layer, is it going to increase or decrease? It is going to increase. Yeah, people are typing increase. But let's assume that this is the optimal that you can do, because this depends upon the data also. No? This also depends upon the data. So if the data is such that you cannot get more than some accuracy, so increasing the number of layers may not help you. Make sense? So let's assume that this was the best architecture. Let's assume that this was the best architecture. So if I further increase the number of layer, what should happen? Accuracy should not reduce. Okay, it should be, if it is not increasing, it should not reduce. Okay, so if you understand this idea, then you would also understand this idea that let's assume that I have a problem P. For that, let's assume 20 layer is the thing that gives you the best thing. But I don't know this number now, because I'm doing the experiment. I don't know that how much layers I need. So what I would do, instead of 20, I put 80 layers, because I don't know. So if I put 80 layers, so at least I would be able to get the accuracy that is equal to 20. Means what? I can safely say that I can get the best accuracy. Okay, so if you increase the number of layers too much, so you are going to be into the better scenario. So the idea of ResNet was this, that you increase the number of layers too much. Nearly 150 layers he have applied, and he trained the system using this kind of systems. However, once again, when we would discuss about the ResNet into the full details into later classes, then I would tell you that even this was not possible. Okay, so there were some other things need to be done to make it work. But the basic idea was this, that increasing the number of layers should not reduce the performance. Something need to be done to back up this. But this is a good idea, that if because people were trying using 21 or 30 layers, if somebody puts 150 layers, his accuracy was actually going to be better, and therefore the error rate falls to 3.6%. This database was difficult, and generally 5% error were actually done by the humans itself, because if you ask from humans to annotate the things, they have 5% error. So if the system becomes better than the 5%, means you can think that now the system is actually overfitting, we don't want to go to that particular thing. In the next year, the best paper award of the CVPR goes to the DenseNet, which actually says that on the same concept he had just extended. We would come back to this at some later point of time with more details. So next year, people talked about that I'm going to increase even more layer. I'm going to have the more dense connections, DenseNet 2017, 2018. Then we have seen the various other architectures, other transformers, unit, and all these kind of architecture that we have seen. So this was a brief history of neural network, and right now we are into the area, into the time when we can see transformers, and the transformers are going to be actually the next big thing that many of the time people are going to use. What are the transformers? We would again come to come to these things when we would go and study our computer vision into the more details. Okay, so this was the brief introduction of the neural networks. If you have any question, please let me know. So we have seen this kind of architecture, that a perceptron that we were actually studying into the last class was this kind of architecture where input was there, weights were there, they are multiplied, and on this summation we apply a threshold to, then we put the high or low as an output based on the threshold. A single perceptron can represent many Boolean function. What do I mean by this? Boolean function means the function that gives you 0 or 1, minus 1 plus 1, Boolean function. So how can a single perceptron can represent many Boolean function? Based on the parameter. Okay, if I set the parameter, then it could be this line or this line or this line or this line or this line, any other line. So based on the parameter, it represents a line, and one side there is positive and the other side there is negative, so therefore it is a Boolean function. Any m of n function can be represented by the perceptron. M of n function means what? Actually, m of n function means, let's assume that n is the input. Okay, so let's assume that there are 5 input. Just sake of sorry. So let's assume that there are 5 inputs. Not 5. Let me take n is equal to 4, n is equal to 4. So if n is equal to 4, the input could be x1, x2, x3, x4, and their value could be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, sorry, 0, 1, 1, 1. So this could be the value. So just sake of clarity, let me take only 3. Okay, let me take only 3 values. Okay, let's assume that 3, and if I say that 3 out of 2, this my function is, the function that I am going to define is 2 out of 3, where m is equal to n is equal to 3 and this is equal to 2. If I say 2 out of 3, so it is 3, so here it is 1, here also it is 2, so it is 1, here also it is 2. 2 means what? At 2 places it is 1, na? 2 places. So this is 0, this is 1, this is 0, this is 0, this is 0. So this kind of function, if any kind of this kind of function I make, so a single perceptron would be able to cover that particular thing. Okay. Another interesting idea is this, that 2-layer neural network can represent any Boolean function. Can represent any Boolean function. Once again, what is the Boolean function? Function that has the output as 0 and 1. Boolean function means the function that has the output as 0 and 1. So if I give you any function, Boolean function means I read, for example, x1, x2 bar, any kind of function I can write, for example, that gives the 0 and 1 as an output. Okay, if I write a function like this, so you may think that you can consider it to the SOAP form or POS form, and then you can combine, and only 2-layer of neural network is sufficient to represent any kind of Boolean function. A function that gives 0 and 1 as an output, only 2 layers of the perceptron are sufficient to represent that thing. We would come back to this particular line once again with the more details once the next slide is being covered. I think it would be clear to you. Now I need your help. I am going to give you an example. So let's assume that this is an example. Okay, I am going to give you this example and I want some answer. What is this? Perceptron. X0 is 1. This is by default. As I told you that how many inputs are there? 2 inputs, x1 and x2. X0 is a slack variable that I introduced over here. What is W0? Minus 30. Everybody can see this. W0, what is the weight? W0 is minus 30. What is the weight? W1 is equal to 20. What is the weight? W2 is equal to 20. Make sense? Everybody okay? Now
Yes,
tell
sir.
me, if x1 and x2 I am going to provide 0 0. What is the value of what is the output? 0 or 1? It is a negative value, then it's 0. Make sense? Who is not able to understand? If I put 0 over here, 0 over here, 0 is multiplied by 20, 0 is multiplied by 20 becomes 0, 0 plus 0, and here minus 30. It becomes answer is minus 30. It is negative, then it is 0. Yes?
Yes, sir.
Okay. 0 1, what is the output? Again 0 1, 0 1. 0 is multiplied by 20, 0. This multiplied by 20, minus 30 is minus 10, minus 10 is equal to 0. So here it is 0. If I write 1 0, what is the output? Again 0.
So again
1
0.
1 1, what is the output?
So 1.
1. Great. So this, do you recognize this particular table? What is this function?
And function.
This is AND function. This is AND function. Understand? So with this, I just shown you a weight that can represent as a AND value. Okay, whatever is the input is 0 and 1, then the output would be an AND value. Similarly, if I remove this particular thing, if I remove the x2 and put w0 is equal to minus 10, w0 is equal to minus 10, then it gives once again. So the first line is actually talking about the different thing, and I was talking about the second line. Okay, I was talking about this particular line. Okay, if w0, if you remove the x2, w0 is equal to 10. If w0 is equal to 10 and w2 is equal to minus 20, here instead of 20 it is minus 20. So if I put 0 here, it becomes minus 20 plus 10 minus 20. For the 0 it becomes 1, 1 it becomes 0. Okay, the output becomes 0. So then it becomes a NOT gate. If I change the values in this way, if I say that instead of using minus 30 here, I use minus 10 here, then this particular gate becomes OR gate, because in these places it becomes 1. It becomes OR gate. Means what? Using a right kind of parameter, you can convert this as a logical gate. You can convert it as a logical gate. And from the digital electronics, you know that if this is AND or OR gate, and if I give you any, now you can understand, if I give you any Boolean expression, so that expression you can convert to SOAP form, sum of product. So only product term would be there, and there would be a summation. Product term you can make using and then using OR gate you can find out what is their summation, and by this you can combine using only 2 layers. Okay, in one layer you create the product terms, and then another layer you combine them as an and you get the output. So using this kind of arrangements, you can create any Boolean circuit out of this particular perceptron. So perceptron is very powerful in that particular sense. Makes sense? When you are actually going to combine them as a layer, the multi-layer perceptron are going to be very powerful. However, still XR is not possible. Okay, you cannot. However, XR is not possible with a single. Whenever I am talking about the XR is not possible with a single perceptron. You can make the 2 layers and then it would be possible. So I would stop at this particular moment today. Any questions if you have, I would continue from this particular side into next class. Okay. So till now we have seen that using what is happening. Okay. Till now we have seen that using a perceptron we can make gates, and therefore if we combine them into 2 layers, so any of the Boolean circuit, Boolean output we can get. Make sense? Thank you very much.